Okay. Hello, everybody. Today, today I am sorry, we continue working with optimization using Scipy. And at the end of the lecture, I shall try to give you an example using pyswarms for the sake of optimization. To remind you, Scipy has an optimization subpackage for finding minimum or maximum of a function. This subpackage includes solvers and algorithms for finding local and global optimal values. Anyhow, in order to import the optimize subpackage, you have to write from Scipy import optimize. This is sufficient to import the optimize sub package. Or you can write import Scipy dot optimize as optimize. Or you can also write import Scipy dot optimize as opt. Opt here as alias for optimize, shortened form. This is always possible. In order to import a specific function from the subpackage optimize, you have to put dot after the Scipy and call the optimize subpackage, and then you write import, and after the import you type the name of the method or the function which you want to work with. Today we will do that with another additional 3 methods which are used with Scipy. Yes. The first one we begin with is the minimize-scalar function. So this minimize-scalar function will be called from the optimize subpackage. Firstly, what do we mean by Scipy optimize scalar function? What is the scalar function? A scalar function is a function that takes one or more variables as values as input, but it returns a single output value. We shall take the example which we worked with in the previous lecture. Is squared minus 6x plus 5. So at first, we have to import the optimize subpackage from Scipy, import optimize. Now it is optimized. The second stage is to define our function and what it will return. The function name is f, the variable is x, and it will return x squared minus 6x plus 5. After definition of the function, now we shall call from the optimize subpackage minimize scalar function. So optimize dot minimize scalar of the function which is called or named f as it is here, and this will give us directly the result. Very short expression as you see, very simple, and directly it gives you the answer. If you write print the result, so you will get all the information available about the solution as arranged by Scipy. So you will have a message telling you that the process has terminated successfully or unsuccessfully. Yes, it gives you the value of the function at the minimum coordinates. It is -4 here. And it gives you also the coordinate x where the minimum occurs, which is 3. Here it is 2.9999, approximately 3. Why this is not exactly 3? Because we are going here through an iterative process. The answer may not be exactly 3, but around it. I also told you in the previous lecture that I may be interested only with the value of the x coordinate where the minimum takes place. So I ask the program to print the result dot x. Dot x means from the result, you will call only the value of x. Here it is result x in a new line is given as 2.999. Also, you can require from the program to give you the value of the function at the minimum coordinate. So you print result dot function. You will have from the result the value of the function at the minimum, -4. Here I did not draw the function because you have it in the previous lecture. It is for the same function. And of course, we have the same answers. But I am just illustrating to you how we can use the minimize-scalar function and how we call it from the optimize function. Another activity with Scipy is to use some of the methods available there within the minimize function. It has a minimize function, and through it we can call one of the methods which could be used there. I have shown you yesterday a list of these methods, and I told you you can refer to them to understand the specifications of each one and how it is used and when it is used. For example, here, BFGS algorithm or method is an iterative method for solving unconstrained nonlinear optimization problems. Here we do not have any constraint for our function, so it is applicable, and it is nonlinear, so it is applicable. So we can use BFGS method directly. How to do that? We import numpy as np. From Scipy, we call the optimize function sub package, and from it we import the minimize function. Scipy.optimize, from Scipy.optimize, import minimize. We give the initial guess to the iterative process, as a variable called x0, and we assign for it a value 0. So the iteration begins with a value equal to 0. Now we define our function as we did in the previous example. Now we want to have the result, so we write minimize. And now the minimize function has arguments here. First of all, you need to write the name of the function. Here I gave it a name func, func instead of f. The initial guess x0. And you define the method you want to work. Method equal between two primes BFGS. And that's it. Now there is, if you print the result here, RAS or result, you will get the answer. So print, here I asked only x result dot x. So we will have here somewhere the result, here it is, result x equal to 3. This is the coordinate of the function where the optimal or the minimum occurs. I can ask again to print all the data available about the solution. So I will be given also, as you see, all the detailed answer and figures, values, which are to be displayed. If you compare between this case and the upper one case, here, x, for example, is given as a value, 2.999. Here also x is given, but it is given as an element of a list. It makes no difference. It is the same answer, but this is the arrangement which is here. It gives you, for example, the Hessian inverse, the Jacobian, number of evaluations, and so on. And also, it seems that I have asked the program to print the function minimum value, which means result dot function. It gave me a -4. So the same answer I got here in this example as I have got in the previous one. As you see, there is versatility here with the Scipy, and you can really use many different methods or functions to get the same answer. The last example also I want to show you here is how to use the f minimum function, fmin function. This function could be called also from the optimize subpackage directly. So at first I have to import the optimize subpackage from Scipy. From Scipy, import optimize. Then I give an initial or guess value, x0 equal to 20, for example. And I define the function which I am going to find its minimum. And then I write the instruction through which I find the minimum. Optimize, I call from it if minimum function, and this function must include the name of the function itself, fun_c, and the initial value of 0 only. And now when I print res, or the result, I will get also the result is equal to 3. And the minimum value of the function is -4, and the number of iterations is 21, and so on. Really, I cannot, in this course, demonstrate with you all the possible or the existing functions or methods which are included in Scipy. There are a lot. And many of them give the same answer, and many of them have a specific application. So for those who will go deep in this subject, you have the chance to go, as I showed you yesterday, to go to the reference to the Scipy site and know more about all these functions and methods. And there you may find also examples, how to solve them. Now I am going also to talk with you about another solution for the same function, but by using an algorithm of pyswarms, Python swarms, pyswarms algorithm. This is based on Python also. Before implementing this algorithm to find the minimum, I want to brief you a little bit about pyswarms, what they are and what they do. At first, I have to tell you that pyswarms or particle swarm optimization depends on iteration processes. And you need for this to give the algorithm a set of values which represent candidates for the solution of the given process. And when the iterative process works, these values change in a direction to converge at the end to the most accurate solution. So we have to be keen when selecting some of the parameters of this algorithm so that to guarantee a convergence of the process. Python swarms are bio-inspired, and the philosophy behind them is taken from the swarms of birds or swarms of fishes or swarms of bees, natural creatures which behave in a manner to give an optimization of a problem. Generally, pyswarms or PSOs, particle swarm optimization, is used to tackle continuous optimization problems. And the system here, or the algorithm, is initialized by setting a random potential values to be candidate solutions. Then the algorithm performs the search for the optimum solution iteratively by swarms following the best particle. The essence of pyswarms, of course, depends on using the particles or the elements of the swarm, on using these elements, and each of these elements has some intelligence or information about the problem under consideration. And while doing the search and at each iteration process, at each iteration stage, the knowledge of each of these particles, of course, changes, and its position in the search space accordingly changes. And each particle benefits of its knowledge and also benefits of the information with the neighboring particle. So we have two sources of information or intelligence: the best position information of the given particle and the best position of the whole or global knowledge, global of the position of the whole swarm. Of course, the particles should not depend on their own information only, on their own intelligence only. Otherwise, they will not benefit from the intelligence of the other pyswarms, and the process may not converge or may take a long time to converge. Anyhow, when we talk about pyswarm applications, I am not going to go to the theory and to prove to you how it works. My task here is to explain to you how to use it and the most important descriptive elements so that you can manage these pyswarms effectively and correctly. So the most important here is the effect of the population or candidate solutions size. How many particles are there in the algorithm? This is decided by the engineer himself. You have to decide the appropriate number of particles, the size of the population. Of course, as the size of population becomes more or increases, the knowledge there becomes more and more. But the time taken by this swarm to cover and search all the space takes more time of the computer. So a large swarm, a large number of the particles of the swarm allows larger parts of the search space to be covered by iteration, per iteration. Yes. But this takes a longer time of the CPU of the computer. So we cannot increase the number as we want. Otherwise, the process will take maybe, instead of 2 or 1 or 3 minutes, it may take 5 or 10 or 20 minutes, which is not applicable. Generally, talking about the size of the population here, the recommended figures is to select the number between 10 to 30 particles. And if you need to increase it more than that, you must have some justification for it. Why? Because, as I said to you, this may take a long time of the computer to carry out all the possible iterations. The other effect here, element which affects the behavior of the pyswarm, is what we call the inertia weight, W. And this inertia weight really affects the particle's global and local search ability. Remember that the iteration process of the pyswarms is a stochastic process, and stochastic theory shows, as a result of deep analysis, that this inertia weight range is between 0 and 1, and the engineer has to select the value between 0 and 1. When this weight is small, the PSO algorithm hardly converges, and the success rate is low. So if it is about 0, you have to be afraid that there is no conversion happens. Or along with the increase of W, PSO algorithm has a better convergence and has a better stability. And has a better stability. The other element which also of interest is the number of iterations. How many iterations we need to include in the algorithm. Really, this is also the choice of the engineer. And it depends on the problem we are addressing. If the problem is complex, so you may need a higher number of iterations. But sometimes you find when you draw the cost function, you find maybe it is not required to have this number of iterations. Maybe it is sufficient to decrease it to 100 iterations instead of having 1,000 iterations. This is seen for you because the process is converging and giving you the answer, the minimum value, at 100 iterations, and thus you do not need to iterate more and more, which is not required. In other situations, when you get the result of the pyswarm application, you get the cost function is high, which means the error is high and the accuracy is not acceptable. This is an indicator that the number of iterations which you introduced in the algorithm is not sufficient. And this is not difficult to do. You can increase the number of iterations and repeat the run of the process, and certainly you will find a better accuracy at the end of the iterative process. Another very important coefficient included in the algorithm of the pyswarms is the acceleration coefficients, or they are called learning factors or trust parameters, and they are given as C1 and C2. C1 expresses how much the confidence of a particle has in itself, to which degree the particle believes that it's right, while C2 expresses how much confidence a particle has in its neighbors. Anyhow, shortly speaking, the recommendation here also, according to the analysis done, to select C1 and C2 to be as possible close to each other. And secondly, the range of change of both is from 0 to 1 only. If C1 is much more than C2, it means each particle has much more attracted to its own personal best position, and it is not benefiting from the experience of the neighboring particles. This results in successive wandering. So low values of C1 and C2 result in smooth particle trajectories, and this is not bad, allowing particles to roam far from a good regions to explore before being pulled back towards a good region. So selecting C1 and C2 around 0 is not recommended also. It is recommended to have them in the region of 0.3, 0.4, 0.5, 0.6, but not 0.1, for example. Yes. Anyhow, a number of theoretical studies has shown that convergence behavior of the particle swarm optimization algorithm is sensitive to the values of inertia weight, which is W, and the acceleration coefficients, which are C1 and Cu. Now I shall try to use the same function which we used before in the previous examples, and to find its minimum by using the pyswarms. Pyswarms we shall use also for the sake of comparison to find the minimum of other functions in the coming examples. So, first of all, what we need to import in order to work with the PSO algorithm. I advise you always to import NumPy as NP because very often it is required in most of the activities we do. And if we want to draw a curve or a plot, so we need to import matplotlib library so that we can make the plot which we need. When working with pyswarms, we always need, and I shall show you in the future, how to draw the plot which represents the trajectory of the particles during the iterative process. This image which you get gives you trust and faith with how the elements move and how they converge. So you need always to import matplotlib as PLT. And the most important thing here to import is the pyswarms package itself. So here we import pyswarms as PS. Instead of writing pyswarms always, we shall write PS. What does this mean? This means that pyswarms must be already installed on the computer. How to get the pyswarms? I advise you, if you have time and you are interested with this subject and want to go in depth, to be familiar with the Anaconda organization site, Anaconda. The Anaconda site has hundreds of packages which are based on Python and used with Python. And from there, you can install any package you need. Let me demonstrate this with you for the pyswarms before running the program. So how we install pyswarms? I go, look here down, I go to the Anaconda software and I want to open the Anaconda navigator. It takes some time, about 1 minute it takes, but no problem. This is because the number of packages which are there is very, very high number. Now it is opening, as you see this green, initiating, Anaconda navigator initiation. Okay. Adding featured channels to the navigator. It is adding so that you can see the channels which are there and the packages which you may be interested with. You have to be patient for a while because I told you it takes some time, about 1 minute it takes. Okay. Loading the applications which are there. And now we have the main page here, Anaconda Navigator. If you want to install a package, of course, you have to know in advance its name, or you will go now, as I will do, and look at the packages which exist in Anaconda and select one with interest. I go to environments and open it, click it, environments. Now it is opening. Here, as you see, the channels. And here some of the applications of preference are shown on this page, but this doesn't mean that only these which exist. Now here, as you see, you have this list. Installed, if you press this arrow here, you will get installed packages, not installed packages, updatable packages, selected or all. I want installed because for me, the pyswarms already is installed. So I have here checked the installed, and I want to see the pyswarms. The names are arranged alphabetically. So I go down to the P letter. It will be very near to Python. Also, Python could be installed from here. Here is L, M, N, O, P, here P. So Py, now we are very close to Python. PyL, PyQ. Here is the pyswarms. Here pyswarms with a letter S. What does this mean? This means that there is two packages. One is called pyswarm and one is called pyswarms. Pyswarm was the package which was created earlier than pyswarms, but nowadays, as I know, pyswarms is more perfect and contemporary, yes, algorithm. Of course, here you see Python. So when you want to work with one of them, now it is checked. This means that it is installed. If it is not installed, you have to go, for example, to the not installed. Now you will see a list of packages which are not installed. For example, analfipy or analyst, anaflow. I don't know what it is. What does it mean? There are hundreds of packages. All what you need, if you are interested with one of them, you have to click the square here to mark it, mark for specific version if you want. You press on the version you want, you press on the apply, and it will install. It will install. Now this is not our target, so I go outside this environment. But as I told you, I advise you to know more about Anaconda and the Conda itself and how it works in order to be able to download any package you want related to Python. So what we have done just now, we have imported the NumPy package as NP, we have imported matplotlib as PLT, and we import pyswarms because they are existing in my computer. Of course, I can see where they are included. I can go to in my system and search for them. I don't know. This is the PC. I go to the C, users, Dell. Here is Anaconda. Under Anaconda, I have downloaded Anaconda 3. Anaconda 3. Now in Anaconda 3, there should be packages Here it is. And one of these packages is the pyswarms and pyswarm also. I have downloaded, installed both A, B, C, D, E, F, D, P. We go to the P, L, M, N, O, P, N, O, P, 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 E, pi, pi C, pi D, pi Q, Python. Here is Python, as you see, and ST, here is pyswarms. Here is pyswarms. The version is 1.3. And also we have downloaded pyswarm with another version. So, as you see, it depends on what you want to do. But yeah, now my duty here is to explain to you how to go, how to move through it, and how to find it. So now we have pyswarms, we have imported pyswarms, we want to work with pyswarms. So here, an instruction specifically written from pyswarms, utils, plotters, import function. I have imported the function here, which includes plot, cost history. You can plot how the minimum value changes by iterations. At each iteration, what is the value? It is plotted as a plot. Or you can plot a contour where you want the particles to move, and you can see how they move in a contour plane plot, or you can plot a surface. Here, the pyswarms includes a sub-package called utilities, and the utilities include sub-package called plotters. In the plotters, from the plotters, you import the plot. Plotters, you import the plot, cost history, or plot contour, or plot surface. Really, we are not going to use the three now. We are going to use only plot cost history, but I have kept them just because they may be needed in the future. So now we have imported a function which can plot the changes of the minimum value, which is the cost, yes, by iterations. The next step is to define the function. Okay, I have called the function Ali, and the variable here is x, which represents a list. The first position x of 0 is called x1, and I have rewritten my function x1 squared minus 6x1 plus 5. This is the same expression of the function which we used before. Now we imported all the required packages and modules. We have defined or requested, imported the plotting function. We have defined the function which we are going to minimize. And now we are asked by the pyswarm to introduce or to give parameters which organize the work of the particle which I have mentioned for you. So you have to select, this is given as a dictionary in Python. The keys C1 and C2 and W are given to you in quotations. And these values, I gave them in order to work perfect. So C1 is equal to dot 3. This is the acceleration coefficient. This is the second acceleration coefficient, dot 5. Both of them less than 1. And the weight is given dot 8, which is not that high and not that small. Now I want to make optimization of this function. So I call from the algorithm, from the pyswarms, here pyswarms PS. I imported pyswarms as PS. So from PS, I imported single subpackage. Single, which means that I want to optimize a problem with a single objective function. Why? Because you can optimize a problem with two or more objective functions. That is another thing. So this is our option here, single optimization, single function to be optimized. And then I am calling the optimization function here, which is it is called global best PSO. Note here how it is written. Big capital letters for G, B, P. Global best PSO. This function, which will minimize the process, this function which will minimize our given objective function. What does this function require? It requires from you to decide what is the number of particles you will use. I have selected 25. What is the number of the dimensions? I will use only one dimension, one variable. What are the options? The options are these, which I have already selected. So options is equal to options which are here. Dimensions is equal to 1 because I have one variable. And the number of particles I introduced 25. Now everything is done. Now I want to ask the program to draw for me or to show me the required information. Here I am calling the optimizer. Here is the optimizer. This is the optimizer. I am calling the optimizer to optimize Ali, the name of the function, and the number of iterations which are suggested. I have suggested 200 iterations. The end, I want to plot the cost history. So I plot cost history. What does it require? It requires to be imported here from the plotters. So optimizer, from the optimizer, give me the cost history. It gives me the cost history. It is called a variable cost history, which is going to be plotted. Of course, I can write an additional line, optimizer dot cost history equal cost history. Then I write a new line, plot cost history. It's the same. At the end, we have to write, in order to see the plot PLT show. PLT here, show is an instruction, a function in the PLT, so that it can show me the plot. When I run the program now, I shall get the following information. As you see here, this is not done by me. This is information given from the system. It shows me that C1 I get dot 3. Here it is given dot 3, and for C1 equal dot 3, C2 equal dot 5, and the weight equal dot 8. What I have get, the best cost is equal to -4. So the minimum value, the best minimum value is -4, as we used to have before. The position, the coordinates where this best value appears is the best position, which is 2.9999. So as you see now, the plot here, which shows the cost function and how it changes by iterations, and the number of iterations which I have given 200, and the system is working and giving me that these values, but I can really shorten the value of iterations to 25 and get the same value, -4, and no need to spend more time in the computer. But this is just to show you what's going on. So I want to tell you one thing, that using pyswarms itself is really a very interesting thing and requires from you, of course, to understand in good depth more specific information regarding the behavior of the pyswarms and how they work. But I will try my best. I have prepared for you maybe 3 to 4 to 5 examples where also I am going to animate the motion of the particles within the swarms for each iteration so that you can feel what is going on. But this is given to you now for two purposes. The first reason is we are going to deal with pyswarms in the coming maybe 1 week or through 1 week or 2 weeks. So now I have gave you some basic information about pyswarms. For those who are interested now can build on and can know more about it. And now also you can go through this example slowly by yourself, or you can run it on your notebook newly and see what you can receive. It will, of course, it will give you the same result because I am sure that here everything is okay and there is no problems with this program. Okay, with this, I think I will finish today's lecture with Scipy and with Python swarms. And in the next lecture, I shall try to give you another interesting information regarding the differentiation or derivations which takes place for finding the minimum values. Because you remember I have maybe in the second lecture told you that the basic ideas behind finding minimum of functions really are divided into two groups, two major groups, let me say. One of them which makes use of the derivatives, first order derivatives, second order derivatives, or the other part which makes use of iterative processes and algorithms which are built on this basis. So the next lecture will be on the derivatives and how to find derivatives and how to work with derivatives in order to also understand more and more about the gradient descent method applications also in the coming lectures. Okay, with this we finish and hoping you the best. Wishing you a nice day. Bye.